Okay, well, first, thank you for having me. I'm Victor, and as you probably know by now, my presentation will be in English as my understanding of the Polish language is somewhat lacking. I'm from the Netherlands, where I work for a company called Coolblue, and before I get down to the subject of my presentation, Hypermedia APIs, I want to tell you a bit about Coolblue so you understand why we're working on this stuff. Coolblue is one of the largest online retailers in the Netherlands. We're #1 in consumer electronics in the Netherlands and Belgium. And the reason we are is because we have a ridiculous obsessive focus on customer service. And one of the ways we do that is by also opening physical stores. So if someone doesn't like our web shops, they have a place where they can throw a brick through a window. Now, in order to control every aspect of every process that's basically between the customer first coming to our website and us delivering the package, is doing everything yourself, and that includes development. And we've been growing quite spectacularly, but one of the issues we've been facing is getting a lot of growing our development department, and that's why we partnered up with Yellow here in Poland to find developers as well. So now you know how I ended up here. Yes, so enough with the marketing, let's get down to some IT stuff. Our challenge. In order to sell those products, we have two systems, one of which is our back office, which basically powers everything that happens within Coolblue, from logistics, entering product information. Everything is done within this back office system. It's a Windows application written in Delphi and .NET, which connects to a large Oracle database, and basically it's roughly 400 or 500 clients talking to the same Oracle database. Then there's the web shops. Similar model. We have a cluster of web servers all connecting to the same MySQL database, which houses a subset of the data that we have in our back office. So basically what you can hear here is we have bottlenecks, these databases. And the problem with databases is they're very difficult to scale. With Oracle, we already have a cluster running. With MySQL, we already use master-master replication. But there's only so much you can do to make a database server scale up. You can add SSDs, add more RAM, but at one point you're just hitting the limits. Then there are some other issues as well. The MySQL database, like I said, houses a subset of the Oracle database, so we need to synchronize that data. And that means, because you're operating on the same data in two different systems, there's going to be duplicate logic being implemented in the back office and similar logic being implemented in the web shop software. And then you have all this functionality, all this data, and you want to expose it to third parties. For example, distributors who want to look into your warehousing information or whatever. It's very difficult to get that to your partners when you have it spread across two systems. So how to tackle that scalability challenge? Well, we want to move to a distributed system, and a distributed system will allow us to take the best possible database for every piece of data we have. For example, product information could perhaps better be stored in a document database than a relational database. Pricing you do probably want in a relational database, and so on. You can pick your storage engine a lot better if you don't have to rely on that single database you decided to use. So a distributed system now. Challenge accepted, because that's kind of difficult. You have these monolithic, really big systems, and you want to start taking them apart and move them into a distributed system. So how are you going to take on this approach? What would be a good example of a distributed system that works well? Because this is going to be quite the investment, so you don't want to invest in some approach that will turn out to be, well, not the right one. Well, when you start thinking about it, what distributed system has been able to keep up with its growth quite well is the web. And the web offers us lots of beautiful things. Yes, I'm using memes as well to make a joke here, let's move on. One other thing is, for example, a web shop, and I'm not just doing this to shamelessly plug the Coolblue logo. I want to use this as an example. Let's say you go out shopping and you want that new iPhone. You're going to have a difficult time because all of it is in Dutch, but let's assume that you don't need that. So, I'm going a bit ahead of myself. You end up at a web shop and you look for the product you want. You want the iPhone, so you click on it, you go to the product page, you add it to the shopping cart, and then you proceed to, well, you enter your shipping information, you pay for it, and voila. Now, you could have done this on any other web shop. One of ours, you could have gone to Amazon or a Polish web shop, which I really couldn't mention. But really, the way you use a website, there's a lot of decoupling going on, because all you do is click links, you enter some forms, and the same domain knowledge you have in buying this product, knowing about the concept of a product, knowing to add it to a shopping cart, entering your shipping information, address, performing a payment, all that can be applied to any web shop. So there's no coupling between you as a user and one of our web shops or one of our competitors' web shops. In fact, if you start looking at the entire component set, the entire stack, you could have done this in Google Chrome, in Firefox, in Internet Explorer, Safari. You could have used any browser. And the web server that was powering this web shop, it could have been Apache, Nginx, Lydie, whatever you want to use. So all these components are all interchangeable. And that's pretty neat if you look for a system that you want to be able to evolve, where you want to be able to interchange components. So that's pretty cool. And it's no coincidence the web works this way, because it was designed according to a set of principles and constraints which basically make this all possible. And these principles are called, well, the architectural style is called REST. And some of you may already have heard of it. Most of you might know REST as, oh, I don't use SOAP, I do GET and POST, and I pass some JSON data around, and I have a RESTful application. And that's not that weird, because REST is usually explained wrong. So what I want to do now is just go through these principles and these constraints, so we really get a good focus on what REST really is. REST was written by this man. This is Roy Fielding, and in 2000 he wrote a doctoral dissertation in which he outlined the principles that power the web. And the way what he was trying to achieve was trading in short-term efficiency for software longevity and scalability. And he has a point, because the web was started off on this machine. Actually, this is the first web server ever, and that was, well, over 20 years ago, and we're still using it on, well, something that at that point would probably look like something from Star Trek. So he has a point. So how does he make this work? How does the web work the way it does? REST defines a few simple constraints, one of which is a client-server model. Now there's a whole range of network architectures you can use. There's peer-to-peer, which is probably the obvious opposite of this. But client-server is very basic. It's just a TCP connection or whatever between a client and a server. There's also a clear separation of concerns, because the client can focus on the UI, focus on application state, and the server just, well, concerns itself with processing data and storing it, and there's a clear separation of concerns here. And we'll get to it later, but these two need to communicate through a uniform interface. So, they agreed on a specific protocol which they both will use, so they can be interchanged from one another. Now this protocol, it also has to be stateless. And a stateless protocol has the benefit of allowing for scalability. As soon as the server needs to know about the clients that are connected to it, there's a big limit on what that server will be able to handle. Also, the client will be tied to a single server, because if it were to hop to the next server, then, well, the state would have been gone, and well, you'd lose all the information in your application. So that's something that HTTP is all about, is this statelessness. There's, in every single request you make, all the information that's needed for the server to process your request, it's included in the message. Cacheable. The responses have to be cacheable. And the reason for this is, again, scalability. If you don't need to do a request, and well, it saves resources on the server, it improves the performance of the application, there's a clear benefit. But there's also a downside. Cached data is less reliable, because you're using something that might not be true anymore. So there's, to every upside, there's a downside. Another constraint is the fact that it's a layered system. The client doesn't know whether or not it's connected to the actual end server. There could be a proxy server in between, or a load balancer, or a firewall, or whatever. The client doesn't need to know about this, so there can be a hierarchy of systems. And each component in between, each intermediary system, can offer clear added functionality, such as a load balancer, which allows the client to connect to, well, a whole pool of servers, or a proxy, which might offer caching, or some kind of content filtering, or whatever. There's benefits to each of these components, but again, there's a downside. Each hop adds latency, so you need to make a trade-off, and that's what this style is all about. Code on demand, then. That's the only optional constraint in REST, and it's been pretty powerful in the web, because what it does, it allows the server to offer the client code which it can execute within its context. And you should think of JavaScript or Java applets, Flash content, Silverlight content, all that stuff. It basically enhances the functionality of the client without the client having needing to have any prior knowledge of what it might receive. So there's a clear upside, the extensibility of the client. However, there's a downside as well, because the client doesn't actually know what functionality it's offering to its end user. And, well, you only need to look at some security websites to see what that does to Internet Explorer or whatever. People have found interesting ways to use this feature. So the uniform interface I mentioned earlier, and this is really key in what makes it so powerful. It wasn't just in the whole visual aspect, because as you as a human are capable of recognizing certain elements, the add to cart button, knowing how to click a product, and proceeding through, well, any web shop really, or website for that matter. That's because of this uniform interface. And it also works on the protocol level. Now REST has a few sub-constraints of this constraint, and one of them in this uniform interface is the identification of resources. And basically these are two things. One, a resource. And a resource is a very abstract concept in REST. A resource basically is any data that can be addressed. And it can be today's weather, or a news article, or some YouTube video where a Korean man is pretending to ride a horse. Anything can be a resource. And this resource has to be uniquely identified, or identifiable. And this, well, happens through let's call it a uniform resource identifier. The manipulation of these resources through representations. And that's an important concept to think about, because the way the data is stored on the server isn't necessarily how it is transferred to the client. They're conceptually different. The data on the server, it might be in some relational database, but you never send out a dump of your database to the client and then expect it to do something with it. It's transferred through a representation, which might be HTML or a JPEG or whatever. So there's a decoupling there between the format that's used to transfer the data to the client and the way it's stored on the server, or from the client to the server. As I mentioned before, it's a stateless protocol, so it needs self-descripted messages. And what that means is that all the data that the server needs to process a request is included in the message. And this includes also metadata that describes the actual message body. So there's a content type header, for example, in HTTP, which describes what's actually in the message body. And it has caching headers and all kinds of information, so the client knows how to deal with message. And then there's this. This is Hypermedia, is the engine of application state. Or as I like to call it, the worst abbreviation ever. So Hypermedia is the engine of application state. It's quite a mouthful, and it's basically the key driver behind the decoupling between the client and the server. Because it's Well, before I get to that, let me first explain an important difference about application state and resource state. The server maintains the resource state, so that's just storing well, whatever content you're offering. The client maintains application state, and that's a lot broader than the resource state. Application state may consist of data from multiple resources. For example, if you load a web page, it's not just the HTML that you downloaded from the server, it's also style sheets and images and JavaScript. So it's combining all these different resources into application state. And as soon as you start entering data into a form, you actually change that application state already without affecting the resource state. So it's important to see that distinction between the two. So Hypermedia apparently powers this application state, or that's what the constraint is all about. So if we look at our client, it's basically a state machine. When you enter a web page, you enter its first state, and then you want to move to a different state. So how does that happen? Well, it takes a representation from the server, which is usually an HTML page, and you transfer from one state to the next, from the index page to the product page to the shopping cart, and so on. These are all state transitions, hence REST, or representational state transfer. Your client, its application state, changes through these requests. But how does it know which state transitions are available? Because the client needs to know somehow what state transitions are available to it. Now, if we were to hard code this into our client some way, then there would be massive decoupling or coupling. You'd have to, download a sitemap or something into the client so it knows all the URLs and you know where to go. And that's usually how RESTful services are being done in most cases, is the client somehow has some out-of-band information available as to what URLs are available to it. But when I just entered our web shop, I didn't know in advance what the URL of the iPhone 5 page would be. I just clicked a link, and that's Hypermedia. Hypermedia is just the notion of hyperlinks and hypermedia controls such as forms. So the server somehow is dictating where I can go. Hypermedia is the engine of application state. It's a server telling me where I can and cannot go. Now, we've been doing this quite successful for people, for humans. And the web has mostly been targeted at humans. We've tried to make it more accessible to machines through micro formats or schema.org and RDF and the whole semantic web movement. But still, machines are a second-class citizen. And Wally doesn't approve. So what if we were to take all these properties that the web offers us and start targeting it at machines? And all of a sudden, we have these tried and proven principles that make the web, well, makes it humming along for over 20 years now. And we can build an API which can naturally evolve, where we can introduce new technologies with skills on, well, a planetary level, basically. So, we thought, well, let's give it a go. And that's what I want to do here now. I believe I still have some time to do that. Let's model the steps we took earlier in a machine-targeted approach. So what we did was we found a product, we added it to our shopping cart, we created an order, we provided our shipping information so we knew where to send it, and we paid for it, and off it went. So we need a few components. First of all, HTTP. Now, HTTP isn't necessarily tied to REST, but it's really the only protocol that actually implements a principle, so it makes sense to use HTTP because it's RESTful right out of the box. But be careful, because HTTP isn't necessarily confining you to these constraints. You can easily use it to build something that isn't RESTful. It violates all these principles. For example, if you use SOAP over HTTP, that has nothing to do with RESTfulness, or cookies, for example, are another great way to violate these principles, because it violates the statelessness. So what does HTTP do? It provides the verbs to our nouns. It offers us a set of it provides the verbs to our nouns. It provides a set of methods that we can use to operate on our domain data, our nouns, the concepts we have in our application domain. And in our case, it's a product, a shopping cart, etc., etc. They're domain specific. They're not written in the HTTP specification or anywhere else. That's where you need to come in, and you need to write them down so the client and the server have something they can agree on. You can do this through documentation. Just write a Word document which states, well, we have a product and it has the following properties, and then we have a shopping cart that has these properties, and these two are somehow related because I can add a product to a shopping cart. This you'll need to write down. You can do that in a Word document, put it somewhere on a network drive and forget about it, or you can use a schema format such as XSD or a JSON schema and have the added benefit of being able to validate your data based on that schema. So I recommend doing the latter. Okay, so we wrote a document which states, well, we have all these domain objects, and now we need some way of transferring them between the client and the server. We need some format. And there's an important thing to keep in mind here, because it needs to be Hypermedia aware, because if you use a format that doesn't support Hypermedia, well, you're going to have a bad time implementing Hypermedia as the engine of application state. So we have HTML, SVG, and Atom, which are all out of the box Hypermedia aware. They have the notion of hyperlinks and hypermedia controls. XML and JSON don't. To XML, there's just, it's just another tag and another attribute. It doesn't define what a hyperlink is. You can use stuff like xlink or xhtml or whatever, but these are all formats that were implemented on XML. XML itself has no notion of hyperlinks, and neither does JSON. So you can use one of these existing formats which does have this notion, or you can create your own and take XML or JSON and start writing a format, and you can basically write a specification. I don't know why you want to do it, but if you have some spare time, go ahead, knock yourself out. It will probably live in the application namespace. If you want to go through the whole trouble of registering it as a public format, where people will probably laugh at you because you've reinvented the wheel, you can just put it in the vendor prefixed media timespace, the VND prefix, and you don't have to go through the registration process and create your own format. There's one small benefit to this, is that it allows you to tie your format to your domain schema. You could do that, but you can also implement your schema in any other format. I'm going to use HAL. And HAL stands for Hypertext Application Language. Basically what it does, it gives XML or JSON the notion of hyperlinks. That's all it does. First I'm going to look at a quick example of HAL in JSON. So what we have here is a special property which the HAL specification defines, which is links, and it's prefixed with an underscore, so you have the, you can tell the difference between that property and the rest. Now at the bottom you see some product-specific properties, but let's focus on that links part for now. There are a few links there. One, self, which is mandatory, which will always refer to the current representation of the resource. And there's profile, which points to the schema used to, well, define your properties here. So that schema defines product ID, name, brand, availability, and price as being properties of product. And then there's another one, add to shopping cart, which adds the product to a shopping cart. It uses a URL template, which is also defined in the specification somewhere. Basically, it just tells it that there's a shopping cart ID variable there that can be used. And it says template, it is true to tell you that it has a URL template. Just a quick look at the XML example. It's the same data, only serialized in XML, so there's not a really big difference. Now there's one important thing to note in these links, and that's the rel attribute. The rel attribute tells you what relationship the link represents. Now, again, as a human, when you visit a website, you know that, well, there's a picture of an iPhone there, so I know that it's probably going to lead me to the iPhone 5 product page. It makes sense. But a machine doesn't have that distinction. To a machine, it's all just data, it's strings and integers, and it doesn't really tell it anything. It needs semantics, it needs context, it needs a description, and that's the rel attribute. It defines the relationship of a link. And that's also the primary identifier of a link. Because if you're looking for the link to, I know, the shopping cart, like we just saw, that rel attribute will be able to tell you what link you need to use. And the semantics of this rel attribute are defined in your domain as well. It's not just the objects, but also the relationships that you need to define in your schema. Basically what I just said. You can also use the link to your schema in the content type header returned by the server, so the server knows before inspecting the actual message body what schema was used to form the data. Here's another example. This is a shopping cart. It's very similar. It has links. Self is there, profile is there. It has another link, order, which can be allowed or can be used to order the current shopping cart. And then there's the second optional property of how embedded. And basically what it does is contain other resources. In some cases it makes sense to have the data of other resources available in the representation of the current resource. In this case, the shopping cart lines. Now we could have done something different here. We could have just contained a lot of links to various shopping cart lines, and you'd have to make a request to each and every single resource just to get a list of the contents of a shopping cart. Instead, we went the easy way. We embedded subsets of these resources into the current representation, and that's what you see here. You see a shopping cart line being embedded in the representation of that shopping cart. And then there's the additional property of the total amount in the shopping cart. Okay, so now we've defined the nouns of our domain. We've defined the objects and their relationships, and that's all fine and dandy, but there's nothing you can do to them. You need verbs, you need methods that will allow you to interact with these objects. HTTP defines a few: get, put, delete, post, and there's a few more, but I'll leave those out for time's sake, really. Now, the first three, all four you're probably familiar with, but get, put, and delete have a special property that post doesn't. They're idempotent. Get retrieves data. That's all it does. It should never manipulate data. Sometimes on the web, you have a URL which you can click on, which will add a product to your shopping cart. That's not supposed to happen through get. Get should always only retrieve data, never change it. So that means that no matter how many times you execute that method, nothing will change on the resource state. Put is basically an upsert method. It takes a message body included in the request and it stores it under the URL of the request. If the resource didn't exist, it will be created. If it did exist, it will be updated with the data included. Delete, well, it does what it says on the label, it deletes the resource. And no matter how many times you execute these methods, the result will always be the same. Post, on the other hand, is different. The operation performed by post isn't defined in the HTTP specification. It includes a few suggestions that it may be used to create a message on a message board or whatever. But really, post, all it does is it accepts a message body for processing. And then, well, whatever the server does with it, that's up to you. And that also means that it cannot be idempotent. It cannot guarantee you that no matter how many times you perform this request, the result will always be the same, because you don't know what will happen to it. For example, if you were to put a payment method behind post, you kept repeating the request, you'd just be, well, draining your credit card. Okay, so it's a lot of blah blah blah. Let's do it. Let's just build an Hypermedia API using these principles. Okay, the index page. It's very simple. It's just a list of links like most homepages are. This offers references to our orders, our products, and our shopping carts, but we're interested in products, so we'll go there. And again, we use a URL template here, so you can apply some filters to the product list, because otherwise, if I were to go to the products resource, I would get every single product in the catalog, and it's going a bit too much. So I'm going to filter by brand, the infamous brand Sangsam. And it returns a single product, the Sangsam iClone. So we've now found a product that we want to put into our shopping cart, and first we navigate to that resource. So we perform a get on the method, and we just skip right back. Again, you have the link here to the product resource. You can use that to navigate to that resource, and we get a representation of that product. You saw it before. Includes the add to shopping cart link, which allows us to add it to a shopping cart. Now in this example, I assume that I already have a shopping cart ID, otherwise I would have gone to the shopping carts resource and first create one. So for now, I assume that I already have one. And my schema defines what this relationship, this add to shopping cart resource or link does. It tells me that I need to do a post request, and it also defines the contents of the message body included in that request. And it doesn't contain the product itself, because right here it says 699.95, which is a price in, well, some undisclosed currency. But we don't want the client to actually submit a price to our shopping cart, because there will probably some mysterious discounts going on. So instead we provide it with a URL so the resource can do a request of its own and get the actual price. And then there's the quantity, we just want one. Now the resource was created. We've created a shopping cart line. And this gives us some new information, this resource. We now have a shopping cart line, which also includes a link to the shopping cart, so we know how to get back. And we have a link to the product that we just added. Let's go to the shopping cart. Oh, wait, I keep forgetting that this slide is here. Just so you know how to use delete, like this. Let's pretend we never did. The product is still on our shopping cart. And here we have shopping cart with our SunSam icon in it. Now there are two extra links here. Lines, which will take us to the contents of the shopping cart, and order, which will allow us to navigate to the order resource and create an order based on this shopping cart. Again, our schema defines what this relationship means. It tells us that we need to do a post to orders. We do pretty much the same thing as adding the product to the shopping cart. We provide it with a reference to the shopping cart, so the order resource knows where to find the shopping cart from which to create an order. Now, I left out some stuff, but links contain self-profile, etc. Embedded, there's a line, an order line, which is basically just a copy of the shopping cart line. And then there's some extra information: price, total, address and customer are null. The status of the order is still unprocessed, and the error is missing or invalid information. Now, this is not really information a machine can use, but I just put it in here for well, simplicity's sake, really. For now, we know that we need to add some extra information. This order cannot be processed yet because something's missing. The address and the customer. We use put here to update the resource with the address and the customer. And now all is fine and dandy. The order has an address and a customer, but it's still unprocessed. But if you notice the difference here, we got an extra link, payment, because that's the next step. And the state wasn't available earlier. So that's an important concept of this whole Hypermedia is the engine of application state. It's a server telling the client what it can and cannot do. So if there's any additional business logic which decides whether or not you can do the payment, you can implement this on the server side. You don't have to go to your client and include some extra logic which tells it that no, you still have to, I don't know, run around 3 times before you're allowed to do a payment. Oh, I'm going a bit too fast here. So we now have the payment link available. And again, our schema tells us to do a post here. But I just said you shouldn't be doing posts for payments because you might empty out your credit card. So all we really do here is create a payment transaction using post. So we've created a new transaction. This resource returns a payment. And there's still some information missing: cardholder, and the card number, and the CVC code, and the expiration date. That's the data you usually need to enter to process a credit card payment. And again, it says status unprocessed, missing or invalid information. So let's take care of that. John Doe would like to pay with this fake credit card. And now we've updated the payment. But if something would have gone wrong with this request, for example, we wouldn't have received the response because some network admin just pulled the plug on us, we can easily just keep doing this. We can keep updating it. And the server will know that, well, once it actually has processed the data, it will just keep continuing with replying with 200 OK. But it will only have to execute actual payment itself only once. As soon as it receives the data, it will execute the payment because the order was moved from a error state to a state where it did have the data to continue. And we can all keep this on the server side, and you can just keep repeating it. So you now have a distributed system, which is actually very well capable of handling network failures. Wow. Okay, so we did the payment, status processed, so we've paid for the product, we've paid in full. So now let's check up on our order status. Now, you can see now the payment is also embedded within the order, so we have a nice overview of our order lines. I left them out here. We have our payment, so everything is completed. The status processed. We know that this order was completed and it's probably on our way now. So that's a very basic example of how you could model a somewhat complex process like going through payment and all that using just basically 4 verbs and a clear definition of your nouns and their relationships, your domain concepts and how they relate to one another. So the HTTP specification probably won't be changing anytime soon. They're working on some new protocols, but you can pretty much guarantee that HTTP 1.1 will be around for some time in the near future. Something that will probably change is your domain model. So a product might get some extra fields, something might change, you might need an extra field in payment, whatever. You're going to have to change that at one point. So you'll be able to want to version that. Now, the web has solved this in a pretty clever way by just simply ignoring stuff it doesn't know. You can still use Internet Explorer 4 to access an HTML5 page. You won't get the same experience, but, well, it will probably break because it's Internet Explorer 4, but you know, it will ignore the stuff that it is incapable of handling. So, for example, if you disable JavaScript, a page will still load, it will just simply ignore the script tags. So that's how the web was designed, to ignore the stuff it doesn't know. So if you implement your client in a similar way, but there's an extra field there, I don't know what to do with it, I'll just keep sending it along, but other than that, I ignore it. So you really have to design your client with that concept in mind. And then most of the upgrades, adding fields, that kind of stuff, you'll be able to do that pretty painlessly. But at some point, you'll probably change a field. I know, it used to be an integer, and now it's a string, and everything breaks, and you have to, well, implement versioning in order to make sure stuff still works. Interesting enough, they actually thought about that as well. They have the accept header in HTTP, which basically tells the server what stuff the client can handle and what it cannot handle. Now, I put it on new lines here because else it wouldn't fit on the screen, but this should normally be on a single line. And what you see here are two different media types, although it might look like it's one and the same. Application hell in JSON, and it has a profile for version 2 of the schema, and there's application hell plus JSON with a profile for version 1. Now the important thing to note here is the quality parameter. The Q is 0.8, and that tells the server that I prefer version 2 because it's lacking the quality parameter and the default value is 1, but I'll also be able to handle version 1. So if we haven't upgraded the server yet, and it still runs on version 1 of our schema, it can just simply return version 1, and the client has indicated that we'll be able to process it, so everything will be fine. The other way around, if we've updated the server to version 2, but our client doesn't, well, understand version 2 just yet, it can fall back to version 1. Now this isn't something you'll get out of the box, so you'll have to implement this stuff on your server. It has to be able to handle multiple versions of your schema. But when you're in the midst of upgrading any system, that's a lot smaller effort than it is to simultaneously update all your clients, especially if you don't have any control over some of the clients. For example, you have an iPad app out there that it will have to go through Apple and they have to approve it, and it will take months, and then you can hardly change your schema. So this is a good way to solve that problem. That basically concludes my short introduction to Hypermedia APIs. It's a very broad topic and there's a lot of discussion on it. A good way to familiarize yourself with it is reading Roy Fielding's original dissertation on the whole subject. It's a bit dry, it's academic, and there's a lot of, well, needlessly difficult words because he wants to sound interesting, but it is a good read. So you can find it there. The HTTP specification, it's also not very light reading, but if you want to get into this stuff, you really want to know all the features of the HTTP protocol, so I highly recommend reading it. The URL template specification, wouldn't recommend reading it, but it's interesting nonetheless. And the HAL standard, if you want to familiarize yourself with that. So, that was me, and again, a shameless plug, we're hiring, do it. Thank you. Any questions? Yeah.
When you were describing the payment process,
Yeah.
and there was the first post request to create transaction,
Yeah.
then was the several possible push requests.
What do you mean?
Next, the point is if you update the credit card number several times what happens? So the return an error, or
No, it will keep returning at 200 OK.
and the data would be updated then?
No, that's the beauty of it. On the server side, you can implement all the logic that you want to ensure that this method acts in an idempotent manner. So the first time it doesn't have the data available, as you can see, the card number and all that is still empty. So at that point it is unable to process the data. The first time it receives this put request to update the data. As soon as it has this data, it can move it from a state where it's unable to process it into a state where it is. And then if you just keep updating this resource, the server would still know that I already received this data, so there's nothing I have to do. So although the server doesn't actually do anything, it will keep telling the client, no, it's fine, 200 OK. So on the server, you'll have to implement logic which ensures the fact that you don't do multiple payments. But the client doesn't have to know about any of this. All it has to do is just keep looking for that 200 OK, and as soon as it has it, it knows that it's been completely successful. But really what it is all about is that between you performing this request and getting this response, if someone unplugs the network cable, you will never know that it was successful, despite the fact that the server might have received that data and already went on. So that's why you want to use put, so you can just keep repeating this request until you've received your response. Does that answer your question? Or? So to summarize, it is something you will have to implement on the server, but the put method is intended for idempotent use, so no matter how many times you repeat it, it should result in the same thing. And you have to implement that yourself, but the semantics of this particular method dictate that you do.
But is it important when you provide same request, same data, but when you provide some other credit card number, then there should be an error?
Yeah. If you were to change the transaction with different data after it's been processed, but at that point it's no longer in a state where you want to be able to change that data. So the server would in this case return a 409 conflict response saying that, well, you muppet, you're trying to update a transaction which has already been completed, so you shouldn't. But it shouldn't say 200 OK, because in that case you're actually trying to do something wrong, so it should prevent it. But if you were to keep sending the same data, the response would just keep being 200 OK. Okay. Anyone else?
There are some downsides to this, the whole Hypermedia API, because you can choose REST over this. You can choose that, no, I don't need the Hypermedia and do REST. But if I decided to do this, I see the upside. Yeah, I know the benefit from that, but downsides, some.
Yeah. Well, first of all, it isn't really REST if you don't adhere to the Hypermedia constraint. So technically, Roy Fielding will be out to get you if you call your application RESTful and not implement the Hypermedia constraint. He has a very strong opinion on that. So yeah, if you don't, then you'll be done a lot quicker, because you don't have to write any logic that will go looking for links or anything. So I'm just going to, maybe I should use less slides. Where did I put this? Yeah, short-term efficiency over software. You trade in software efficiency or short-term efficiency, so basically that's what you're doing because you're done quicker, but you'll lose it in the long run in software longevity and scalability. Because if you take out, for example, that component of following links, then at one point you change your URLs or some structure changes, then you have to go through your client and make the same changes. As long as you let the server dictate what the client can and cannot do, there's only one place where you have to change it, and that's the server. So that's the upside, and the downside is that it just takes more time to develop an application. But once you have a solid ground layer or a framework which is able or capable of handling this stuff, then really there's just a lot of upside to it. And if you decide not to go with REST at all, well, if you write an application for high frequency trading, in stock trading. You probably don't want to use HTTP because it's a very bulky and very chatty protocol, so you want something binary that's really fast. But for most applications, a 100 millisecond request or whatever, it doesn't really matter, so then there's just a clear benefit of using this. Also, there's just a lot of off-the-shelf tools you can use to improve your application's performance. You can use proxy servers, you can use load balancers, there's all this stuff that's already available to deal with HTTP. So you get a huge tool set right out of the box by using this. So, that answer your question?
Yes.
Cool. Anyone else?
Thank you, Victor. If you have
Yes,
any other
your question.
You can just catch Victor after official part. Just Victor remain with us.
Yeah. Or send me an email if you think of it.
Thank you very much.
Thank you.